Welcome to section 7.4 on partial fraction decomposition. Okay, so this is an important skill that you're going to learn. You'll use this in calculus next year. So we're going to start off with the basic example of adding two fractions together. Okay, when we do the partial fraction decomposition, you'll then see we're going to do the reverse. We're going to take a fraction and we're going to break it into parts. So we'll start with this warm-up. If we're going to add these two fractions together, you know we need the common denominator, which would be the product of these two denominators. So I'm going to take the 2 and multiply that by x plus 2, and the negative 1 multiplied by the x minus 3, and put all of this over the common denominator. Okay, when I distribute, okay, combine like terms, and I end up with x plus 7. Okay, and then when we multiply the denominator, we get x squared minus x minus 6. So now what we're going to do is we're going to take this fraction and we're going to break it back into parts, into these two parts. Okay, that's the partial fraction decomposition. So here's our starting point. This is an example where there's going to be different types. This is the type where we have distinct linear factors, right? Distinct meaning different. So step 1 is to factor the denominator. So it's the x minus 3, x plus 2. And then I'm going to separate this into two terms using each of these factors as a denominator. Now, in my numerator, I always put an expression that is 1 degree less than the denominator. So since this is first degree, 1 degree less would be a constant, which I'm going to call a. Same thing here, I need a constant, which I'll call b. My next step is to multiply through by the common denominator. So on the left side of my equation, I'm left with x plus 7. On the right, the a gets multiplied by the x plus 2. And the b gets multiplied by the x minus 3. My next step, I'm going to choose values for x that will allow me to solve for a and b. Right? I've got one equation, I've got 3 unknowns. So this method of choosing values of x, such as negative 2, will make the a drop out, and I'll be able to solve for b. So I'm going to let x equal negative 2, and every x gets replaced with that negative 2. So on the left, I now have 5. This becomes 0, and I have b times negative 5. And when I divide, I get b is equal to negative 1. The other value of x I'm going to choose is the value that will make b drop out, and that would be letting x equal 3. When I let x equal 3, on the left I get 10. I get 5 times a, and this becomes 0. So a is equal to 2. Now I have my value of a, my value of b. I can go back to my original setup and plug in those values. So again, the a is replaced by the 2. Okay, so you're seeing here, that's this a. And the b is replaced by the negative 1. Now normally I wouldn't leave it like this. I never have liked that plus minus kind of thing in any equation. But I left it there just for the purpose of you seeing the b as being negative 1. But this certainly could be changed, and in my opinion should be changed, to minus 1 over x plus 1. Okay, so that's the distinct linear factors. I'd like you to try this example. So pause the video, set it up. I'll help you get started. Again, you're going to have a constant over each factor. Multiply through by the common denominator. Choose values of x that will make each variable drop out. Solve for the variables, come back and substitute in. Okay, so go ahead and give that a shot. Pause the video and then come back when you're done. Okay, let's see how you did. Hopefully you got this solution. You can check through the work if you didn't and compare my work to your work. Okay, the next type, repeated linear factors. So now when I factor this denominator, I have x and x plus 1 to the second power. So now, again, for every factor, I'm going to have a term. So I'll start with the x. And for each repetition of this factor, I have a term. So I would have an x plus 1 and also an x plus 1 squared. Think about it this way. If you're adding these three fractions together, my common denominator would still be this product, x times x plus 1 to the second power. So I can't assume that either of these is not necessary. Well, you may be saying, why do we need this one? I can't assume that I don't need it. Right? We're breaking this down as much as possible. If I don't need it, then the variable that I put in the numerator will become 0 and it'll drop out. So it'll always work out the way that it should. You just can't assume that you don't need any one particular part of the breakdown. So in this numerator, I'm going to put a, then b, and for this one, c. Now you may be saying, well, wait a minute, if we multiply this out, it's not linear anymore. What you put in the numerator depends upon the degree of the factor. Okay, the fact that it's being repeated does not change what goes in the numerator. So even though this is a repeated factor, the factor itself is linear, which means we put a constant in the numerator. Okay, now we're going to multiply through. I'm actually going to take this out for space. So I have 5x squared plus 20x plus 6. Over here, the a will get multiplied by x plus 1 squared. The b will get multiplied by x and an x plus 1. And the c will just get multiplied by x. Okay, so now let's see what I want to do here. If I let x equal -1, that'll allow me to solve for c. So if this is -1, I get 5 minus 20 plus 6. That becomes 0, 0, and this equals -c. So I have, let's see, 5 minus 20, -15, -9, so 9 is equal to c. Okay, I can also let x equal 0. When I let x equal 0, that will make these two terms drop out. Okay, so over here, I'll just have a, and on this side, these two terms drop out. So a is equal to 6. Okay, now there's nothing else I can choose for x that will allow me to solve for b. Right? There's nothing I can plug in that will make a and c drop out. So what I can do is choose any other number I want. And I can use these values of a and c in my equation. So if I let x equal 1, right, that's a nice easy number to work with. On the left, I get 5 plus 20 plus 6, or 31. On the right, okay, so I'm plugging in 1 for x, so that's 2 squared is 4, times a is 24. I'm using that value of a equal to 6. Plugging 1 into here, I get 2 times 1 times b. Oops. So I get 2b. And then lastly, let's see, plugging in 1 here times c, which is 9, I get 9. Okay, so I get 33 on this side. When I subtract 33, I get negative 2. So b is negative 1. So let's see how I did here. A is 6. Okay, that's this value here. Next is b. Oh, that's a negative 1. I'm going to put my negative there. So b is a negative 1. So again, that negative, let that become the sign here, okay, in between the terms, rather than writing plus a negative, right? We don't want to get into that habit. And lastly, c is 9. And there you go. The nice thing about these problems, well, if you think this is nice, you can always check these by adding these together. If you add these 3 fractions together, you should go back to your original expression. So all of these problems can be checked, which is a nice thing. Okay, the next example. Here's the partial fraction decomposition for, again, repeated linear factors. So I got you started with the setup. And then you continue from here, pause the video, come back when you're done, and we'll compare. Okay, so hopefully you got this solution. Check through my work if you didn't. And make sure you ask questions in class if you have any. The third type, distinct linear and quadratic factors. So here, when we say quadratic factors, we mean irreducible quadratic factors. So for instance, x squared minus 4, that's not a quadratic factor that can be broken down into linear factors. But here, if I factor out x, I have x squared plus 4. This is a quadratic factor because it can no longer be broken down using real numbers. We do not use imaginaries. So I'm going to have 2 terms, one for the linear factor, one for the quadratic factor. Put my constant over the linear factor, and now that I have a quadratic factor, I need a linear plus a constant in my numerator. I may need both of these, I may only need one. Again, if either b or c don't belong as a part of this breakdown, that variable will equal 0 and it will drop out. But again, I can't assume that I don't need bx plus c. Bx plus c is a valid numerator for a quadratic, right? Or it always has to be a lesser degree, lesser by 1 and anything else. Okay, now I'm going to show you a new method for this one. We're still going to multiply through by our common denominator. So here I get ax squared plus 4a. And here I get bx squared plus cx. Now what I'm going to do is group the like terms together. So I have ax squared and bx squared. If I factor out the x squared, my coefficient would be a plus b. And I'm going to rearrange these to put them in order. My middle term is the cx, and my constant is the 4a. So I have this equation on the left set equal to this. In order for these two to be equal, the coefficients must be equal, which means I can set up a system of equations knowing that excuse me, a plus b must equal 3. Right off the bat, I know c, right? C is the only linear term here, so c is equal to 4. And I only have one constant, so I know 4a is equal to 4. So again, these equations just come from comparing the coefficients on the left and the right. So I know a is equal to 1. That's easy to solve. And you'll find a lot of these systems probably will be pretty simple to solve. You may have some tricky ones eventually, but okay, if a is 1, that makes b equal to 2. And there's my 3 values. So I did need both b and c. Let's see if it matches my solution here. Okay, so we have a over x, so that's 1 over x. B is the coefficient of x here, and that's a 2. And 4 for c. Again, you can check these by adding the two fractions together. So try this example of linear and irreducible quadratic. Okay, set it up, pause the video, come back when you're done, and we'll compare. Okay, hopefully you got this solution. If not, compare the work and ask about it in class if you have questions. Okay, the fourth type, repeated quadratic factors. So now I'm going to have, just like with the linear repeated, I need a term for each repetition. So if this were to the third power, I would have 3 terms. Since it's to the second power, I'm going to have 2 terms. One for the factor itself, x squared plus 2, and one for x squared plus 2 to the second power. Okay, so because this is quadratic, I need a linear expression plus a constant. I need a linear plus a constant here as well, because again, it's based upon the degree of the factor. Okay, ignore the fact that it's being repeated. Because if we multiplied this out, we'd have an x to the 4th, right? You don't want to do all that extra work of having a cubic in the numerator, right? That would be way too much. We don't need that. So we need a cx plus d. Now I'm going to multiply through. So the ax plus b, that gets multiplied by an x squared plus 2. The cx plus d, that has the full common denominator. So you could think of it as getting multiplied by 1. When I multiply this out, I get ax cubed plus bx squared plus 2ax plus 2b, 2b or not 2b, haha. And then I'm going to use that method again of comparing coefficients, because I only have one x cubed, which tells me right off the bat a is equal to 8. For my linear terms, I have the 2a, let me change color here for a second, 2ax plus cx. So that tells me that 2a plus c is equal to 13. I know a is 8. So that means c is equal to -3. Okay, I don't have an x squared term on this side, right? That means the coefficient of x squared is a 0, which tells me that b is equal to 0. I don't have a constant on the left, so that tells me I have two constants here. 2b plus d is equal to 0. I already know b is 0, which means d is 0. So my final answer okay, I have the value of a and the value of c. So as I had said before, anything that you don't need will end up equaling 0 and drop out. So we didn't need the b, so it's just 8x. And we didn't need the d, so it's minus 3x. Try this example for repeated quadratic factors. Pause the video, come back when you're done, and we'll compare solutions. Okay, hopefully you got this solution. If not, check the work. And remember again, you can always check by adding the fractions together. Okay, for our last example, we're going to take a look at the type where we have an improper fraction, okay, meaning that our numerator has a higher degree than the denominator. So if the fraction is improper, we first divide, and then we're going to do the partial fraction decomposition on the remainder. So let's start off with the division. This is another reason why you needed to know long division. Okay, so I'm going to start by dividing x squared into x cubed. That goes x times, and then distribute. So I have x cubed plus 3x squared minus 4x. I'm going to change all of the signs, so that becomes a minus, minus, plus. These terms drop out. I have negative x squared plus 3x plus 1. Divide x squared into negative x squared, that's a minus 1. So that's negative x squared minus 3x plus 4. Change the signs. That becomes positive, positive, negative. First terms drop out. I have 6x minus 3. So now I'm going to take that remainder and put it over my denominator. Let's factor that. So it's going to be plus 4 x minus 1. And I'm going to do the partial fraction decomposition of this fraction. So I have distinct linear factors. And put a constant in the numerator, constant in this numerator, and now I'm going to multiply through by the common denominator. And now it's really up to you how you want to solve. For something this simple, I would just let x equal a value. But if you wanted to multiply it out and set up a system, you could do that as well. It's really your choice of what method you prefer. So I'm going to let x equal 1. That'll make a drop out. So over here I have 6 minus 3, which is 3. That drops out, becomes 0, and I get 5b. So b is equal to 3/5. I'm also going to let x equal -4. So plugging in negative 4, I get negative 27 on the left. Over here, this term becomes 0, and I have negative 5a. So a is 27 over 5. So we have fractional values for a and b. We do not write our answers as complex fractions. So here, this is how your answer should look. First of all, key thing, that quotient, remember that becomes the first part of your answer. Okay, so if you're writing this down, if you're doing this in your homework, I would immediately, wherever I was writing my final answer, I would write that down. Okay, we don't have handwritten tests right now, but I used to tell my students, put that on your answer line as soon as you get the quotient. Okay, now here's our value of a, right, 27 over 5, and that's how we write it. Okay, we don't put 27 over 5 in the numerator, we apply it to the entire fraction, so it's like if you had 27 over 5 over x plus 4, think of that as over 1. When we flip and multiply, it's times 1 over x plus 4. So it's 5 times x plus 4 in the denominator, 27 in the numerator. Same thing here. We don't write it as 3/5 over x minus 1. Excuse me. We write it as 3 over 5 times x minus 1. So there's our final solution for our final example. I hope you enjoyed this lesson. I think partial fraction decomposition is a lot of fun, and I hope you do too. I'll see you in class. Have a good day.